Hello, welcome to Noise Management and its Control. This is the third week of this course, and what we plan to do this over this week is basically we will be developing the one dimensional wave equation. But before we talk about one dimensional wave equation, I wanted to cover one more specific topic which is related to transfer functions. So, in this lecture we are going to talk about transfer functions, and then starting from the next lecture and onwards we will be working on the sound propagation and the equation for sound propagation, which is also known as 1D wave equation. So, right now we will discuss transfer functions. Now, earlier we had discussed that we have a system and we can have an input and then there is an output. So, the input is because of some stimulus, and as a consequence of this input or this stimulus, we have the system responds and we measure the response. So, the output is in form of some response. So, for example, there is a cantilever, very simple system. I apply some force, that is my input, and the response will be that the beam or the cantilever is going to deflect. So, the response is deflection. I can have it just the other way around also. I can have an input as a displacement, and then I have to see, and if I can measure how much force is required to produce that deflection. So, that is the response, which is the response of the system. So, this is the context in which we will discuss this notion of transfer function. So, what is a transfer function? So, first we will define it. And this definition, so this is, it is a function, it is a mathematical function which relates the response of the system to the stimulus provided to the system. And at least in context of this course, we will talk about transfer functions. So, this is, it is a mathematical function which relates response of the system to the stimulus provided to the system, and this we will do it. So, this transfer function notion is really useful only for linear systems, and we had discussed what is a linear system and what are the attributes of linear systems in the last class, which is in the last week. So, the systems we will consider are only going to be linear in nature, and also, so it will be and simultaneously they will be time invariant systems. So, what is a time invariant system? Where the physical attributes of the system do not change with time. For instance, a system which is an example of a system which is not time invariant would be, you have a rocket which we use in firecrackers, and we ignite the rocket and the rocket goes up in the air, as it is going out, it is ejecting mass out of it in form of gases. So, the mass of the system as the system is moving upwards is changing. So, that kind of a system is not time invariant, okay, because the physical, some of the physical attributes of the system are changing with time. So, we will talk about transfer functions only in context of linear systems and systems which are linear in nature and simultaneously they are time invariant in nature. Okay. So, this is important to understand. So, transfer function is a mathematical relationship which relates the response of the system to the stimulus provided to the system. So, we will do some examples. First example could be a voltage amplifier. Voltage amplifier. So, what does a voltage amplifier do? It runs on some power source. Okay. So, it requires some energy to make it work. So, it runs on some power source. So, it could be a battery or some 20 volt DC supply, and then what do I do in an amplifier? I excite it with some input, and let us say it is Vi, and then the amplifier amplifies this Vi and it provides an output. So, it is Vo, and where does the energy come from to amplify this input? It comes from the power source. So, the input to the system is Vi and the response of the system is V naught. Now, these are both, they could be functions of time. So, in this case the relationship between V naught and Vi, the relationship between V naught and Vi will be what? It will be called the transfer function. So, let us say Vi is equal to some complex amplitude Vi capital E j omega t, and because the system is linear, what does that mean? That V naught will be some complex amplitude times E j omega t. Okay. And there could be a phase difference between input and output, but that phase difference gets expressed in what component? This complex amplitude part, because we had seen this earlier. The phase component gets into the complex amplitude of Vi and V naught. So, the transfer function for the system, I can express it as H, and that is equal to V naught over Vi, because E j omega t gets cancelled. Now, V naught could change with omega, and so is Vi. Okay. Vi could change with omega. So, these are complex amplitudes. So, V naught and Vi both could depend on omega, which is the excitation frequency. So, H, which is the transfer function, would be itself it can change with omega. So, remember this H is not a ratio, because ratio is what? It is of two numbers, A over B, it is a ratio. Rather, H is a function, it is not just a single number. H is a function which can change with omega. Okay. So, it is a function and it is known as transfer function. So, this is important to understand. Lot of times we by error we say that is the ratio between input and output. but no, the numerator is a function, the denominator is a function. So, it is a function of two other functions. So, in this case, what are the units? Unit of numerator is voltage, unit of denominator is voltage. So, here unit is unitless. So, in this case there are no units for the transfer function, but transfer function need not be unitless in all the cases. So, we will consider another example. So, consider a spring mass dashpot system. So, we have done this example earlier. This is my spring, this is a dashpot, both are connected to a mass which can move on a frictionless surface, and what I am doing is I am exciting it by some force E j omega t. And what I am, and so this is the stiffness of the spring is K, the damping constant is C, and what I am, so this is my excitation input, and what I am interested in figuring out is how much is the displacement. And because this is a linear system, I can say that the displacement will be of a similar form as f naught. So, it will be some constant amplitude times E j omega t. Okay. Now, the governing relation for this equation is m x double dot plus c x dot plus k x is equal to f t, and this is equal to f naught E j omega t. And now, what we do is we plug x t as x naught E j omega t in this equation. So, what we get if we do all the math is minus m omega square plus c j omega plus k x naught E j omega t is equal to f naught E j omega t. So, this is my response, this is my excitation. If I take them one over other, then I get the transfer function is equal to x naught. So, E j omega t gets cancelled from both sides, and this is what 1 over k minus m omega square plus c j omega. Okay. So, once again this is not a single number, it is varying with omega. So, again it is not a transfer ratio, it is a transfer function, that is why we call it a transfer function. And what are the units? In this case the unit of x naught is meters, f naught is newtons. So, the unit of transfer function is meters per Newton. Okay. Now, look at this relation. The transfer function does not depend on f and neither does it depend on x naught, because what do you have in transfer function? It is 1 over k minus m omega square plus c j omega. K is a purely depends on the system, m which is the mass, it again purely depends on the system, and c again purely depends on the system. So, transfer function, at least for linear systems, It purely depends on properties of the system. Okay. It purely depends on properties of the system. This is important to understand. It does not depend on nature of excitation for linear systems. This is important to understand. So, if you know the transfer function, does not matter, whatever is the excitation, you multiply that by transfer function and you will get the response of the system. Okay. Another example, example 3. So, you can have a sound system, some complicated sound system, and you are having a loudspeaker here, and I am giving some input. Okay, I am giving some input into this, and of course, there is a power supply which provides energy, and because of this the sound system is producing sound, and here I have a microphone, and it is measuring P of t. So, what is happening in this case? First thing is that voltage is getting converted into some motion of the loudspeaker, and that motion is getting converted into sound waves, and the sound waves are being measured by microphone as pressure. Okay. If this is a linear system, then the nature of V I and nature of P, it will be the same if it is a linear system. So, in this case H of omega, what will be the unit? It will be pascals per volt, because the response I am measuring in terms of pressure, excitation is coming in form of voltage. So, the point is the transfer function could be unitless, as we saw in case of a linear voltage amplifier, or it could have any other units. In this case it is meters per Newton, in this case it is pascals per volt. But regardless of whatever the system is, the transfer function is essentially, it purely depends on the properties of the system. When the system is linear, it does not depend on the nature of excitation for linear systems. So, associated with transfer functions are terms known as poles and zeros. So, any transfer function. Now, go back to this particular transfer function. So, this we will consider it as an illustration. So, it has in the numerator number 1, and in the denominator it has k minus m omega square plus c j omega, right. So, any transfer function will have a numerator dependent on omega and a denominator dependent on omega. In the case we saw earlier, the numerator was 1 and the denominator was k minus m omega square plus c j omega. Okay. And if it is an algebraic expression dependent on omega, I can factorize. So, if it is an algebraic expression, I can factorize it into lots of linear factors. So, it could be z1 minus omega, z2 minus omega. So, if it is a polynomial of nth degree, then how many factors it will have? It will have n factors. So, zn minus omega. And similarly, if the denominator is a polynomial of mth degree, then it will be p1 minus omega, where p1, p2 are constants, p2 minus omega, pm minus omega. So, poles are roots of denominator. They are roots of the denominator. So, in this case, if we can factorize the denominator as p1 minus omega plus times p2 minus, then all these poles are p1, p2 till pm, and zeros are roots of numerator, and these are z1, z2 and so on so forth till zn. So, if I have any complicated transfer function and if I get my mathematics correct, I can always factorize it in terms of a bunch of linear poles, a bunch of zeros and bunch of poles, and once I have factorized them, I can by variable I can separate them as sum of individual poles and zeros. Right. So, this is another thing I wanted to talk about. So, that concludes our discussion on transfer functions, and with that we close the discussion for today. And what we plan to do tomorrow onwards is we will actually develop the one dimensional wave equation, which will help us understand how sound waves travel in medium and how does pressure move from point A to point B to point C and so on and so forth. So, that is what we plan to do in the remaining part of this week, and with this I close the class for today, and we look forward to seeing you tomorrow. Bye.